34.1. First of all, we're going to learn what is thermochemical equation before we move on to other math. So, thermochemical equation, it look like this. Not only this part, but also this part. Okay, so remember, thermochemical equation, you must have something at the back like this. This one is very important, and also you'll find that thermochemical equation, you got state symbol there as well. So the features of it, okay, you got 3 or 4 features, you may say. First of all, okay, I put it 0, okay. The equations is not necessary under standard conditions, but most of the time we'll talk about standard conditions. So standard conditions, okay, it represent by the fine, okay, this symbol here, okay. This means that, okay, it is under standard conditions, okay, making the whole reactions will be replicable, okay. The others can do it one more times, okay. Second one, okay, the first features, okay. First of all, mass with state symbols, okay. They won't remind you, okay. They won't remind you like other equations. Whenever you are asked to write a thermochemical equations, you must have state symbol for every single chemicals involved in the equations, okay. Second one, okay, must have a Deta H sign at the back, okay. So you must have these sections at the back to show some important information. Number 3, okay, you got positive and negative sign, okay. I don't care it is positive, okay. If you say, oh, positive, I can omit it, sorry, you must show it, okay, to show whether there is a endothermic or exothermic reactions, okay. If you remember, positive is endothermic, positive, endothermic, and then negative, that will be exothermic, okay. So let's have a look why we have these kind of features. So first of all, what is standard conditions, okay. Standard conditions means that, okay, the experiments will carry out at that conditions. So everyone, if you try to replicate the experiments and try to confirm whether the data or value obtained is correct by the others or not, you can follow the standard conditions, okay, and then perform the experiment one more time. So we have several things, okay. These kind of features or these criteria, okay, they may affect the results, okay, of the experiments, because you know that energetics is measured energy releasing, okay, or absorbing in the process. So like pressure, temperature, concentration, all these things, they will affect the readings or the final results, okay. So therefore, for pressure, it's pretty easy to understand. For pressure, okay, it have to be 1 atm, okay, or with another unit normally would be atm, okay. For temperature, okay, we talk about 25 degrees Celsius, or in Kelvin scale 289, okay, 298 K, okay. Kelvin scale, in case you don't know what is Kelvin scale, okay, it means that, okay, it will have like equals to the Celsius plus 273. Okay, so if you have like 50 degrees Celsius, if you want to turn it into Kelvin scale, you have to add 273. Okay, so for example, you have like 40 degrees Celsius, so you have 40 plus 273, and then you have like 313 K. Okay, so this is Kelvin scale. So have to be 25 degrees Celsius or 298K, yeah, that's right. So for solutions, okay, without specified, okay, all the concentration of the solution have to be 1 molar dm cube, okay, 1 mole per dm cube, okay. So for the standard state, okay, this will be the most important concepts, okay, standard state, because for the elements or for the compounds that you have, they may exist in many different states. For example, when you have NaCl, you may say, oh, it can be solid state, or NaCl can be gas state as well, okay, but you can see that, okay, NaCl can also be liquid state. You can find out, okay, for different state, there's initial temperature will be different, okay. Obviously, the sodium chloride liquid state will be higher temperature than sodium chloride solid state, is that right? So therefore, we have to confirm one state. Everyone should notice that, okay. So that will be the most stable form at room condition. Room condition will like 25 degrees Celsius, 1 atm, okay, that will be a normal room condition. So for sodium chloride, you'll see that at room condition, most likely that will be sodium chloride solid, Okay, it won't be gas, it won't be liquid, because that require a high temperature to do that. But for the others, okay, I'll just like have a look of some examples on the right hand side. For example, for oxygen, which one would be more stable, O2 or O3? So obviously the answer is O2. Okay, that one, okay, in the air, okay, it will be a molecule form instead of single monoatomic molecules, or it won't be ozone as well. Okay, H and H2, again, H2 will be stable. Graphite and diamond, you may say, oh, diamond is very hard. Yes, true, okay, but most of the time we got graphite. Okay, graphite is a more stable form, okay, for that. For red phosphorus and white phosphorus, these kind of phosphorus, you haven't seen it before, no worry, we seldom ask things like this. Okay, so this one is red phosphorus. For metals, okay, it will be in a solid state like MgNa, okay, like sodium Na, okay, things like that. Okay, or Mg solid, okay, or sodium solid. Okay, so that would be the standard state. So why do we need state symbol? So just have a look of the following examples. So if I have the H2 and O2, and then when we have a exothermic reaction, we do a combustion of H2. Combustion of H2. When we burn the H2, they will have H2O. So you have to remember the product it formed in the process. Normally, they will just give out H2O in gas state. So in the process, you see that, okay, we'll have like negative 241.8 kilojoule per mole. That means every 1 mole, they will release 241.8 kilojoule energy out, okay, to form H2O or gas state. However, if you go from gas state to liquid state, gas to liquid, H2O gas to H2O liquid. In the process, okay, because the gas is further apart, right? The liquid, they are closer to each other. So the particle come close, energy release. So actually addition from gas to liquid, this condensation, they will release an extra energy right there. Okay, so if you write an equation without stating state symbol, if you didn't state the state symbols, I don't know you're going gas state or liquid state. If you go to gas, it will be negative 241.8. But you go to liquid, you need to release extra energy. Release extra energy in the process. So therefore, it will make the value even more negative. So that's why you see that if you don't write the state symbol, okay, the values, okay, delta H at the back, okay, will be different in the process, and or I don't know what state or what status of product you are talking about. So state symbol is very important. Then what does delta H represent? Okay, it represents things like this. First of all, you have positive, negative. Negative means release energy. That is exothermic. Positive means absorb energy. That is endothermic. Okay, so that is the first things. Kilojoule means the unit of the energy given out. So if we're right here is stated that negative 635 kilojoule, that means that in this process, when you have 1 mole of calcium combined with half mole of O2, give out CaO. In this process, they give out 635 kilojoule. But if you go for 2 calcium and 1 O2 and 2 calcium oxide, you just have this equation run 2 times. 1 time, 2 times, and then you make up this one. Is that right? So therefore, negative 635, you will have got 2 times. Okay, you have multiplied this one by 2. You multiply this one by 2. Okay, so in the process, you release double portions of energy. It will make up to negative 127 kilojoule. So this delta H, it means that, okay, in the process, okay, or how the energy change, how the enthalpy change in the process. If we just go for this one once, it will release negative 635. If we go for this 2, then you can multiply this one by 2. Okay, so actually you can further do this equation, like maybe multiply this one by 4, then you have 4Ca plus 2O2, and then you have like 4CaO, then the delta H will then be negative 35 times 4 times. Okay, so this is what does the delta H represent. Okay, so how does the sign represent? Okay, just how we mentioned, okay, negative means releasing energy. So we can have, look, negative 285.8. That means, okay, from H2 to O2, H2 plus O2 become H2O. In the process, it's releasing energy. So in this process, it goes down. But we can reverse this equation. If we go from this side, from H2O, and then I break it up into H2 and O2, electrolysis of water, right? So if you go to the other side, you need to absorb energy. This is electrolysis of water. So you need to absorb energy. So the amount of energy that you have to absorb, remember, if the reactant and product, the enthalpy are the same, like this, enthalpy are the same. So the difference, okay, between these two enthalpy level, okay, it must be the same value. So this one is 285, this one is also 285.8, okay, but this will be releasing energy, so it will be negative. This one will be positive. Okay, so if I say C plus O2 becomes CO2, that will be delta exothermic reaction, right? So let's say just random, say negative 200, okay, kilojoule per mole, things like that. Okay, then if we have CO2 becomes C plus O2, that will then become positive 200 kilojoule per mole. Okay, so on the equation, if you reverse the equation, the sign will also be reversed. Okay, so reverse equation, reverse the sign. Get it? Okay, so quick practice. Okay, so standard enthalpy change of the following reactions, that will be negative 1371. That will be the thermochemical equation. Thermochemical equation like this. If you do like that way, it will be negative 1371. How much heat in kilojoule will be released in each of the following cases? 2 moles of ethanol. So that means this one have to be 2. 6 mole of O2. That means this one have to be times 2. That means this equation run 1 time, 2 times. So basically, you just need to negative 1371 times 2 times. Okay. So for this one, it will be 2742 negative kilojoule. Okay, so what I'm doing right here is just 1371 kilojoule per mole times 2 mole. Okay, so therefore you will find that the value of the unit of mole will be eliminated. Okay, so part B, okay, we have 11.5 of ethanol used. Okay, that means how many mole? I don't know. Okay, anyway, 11.5, okay, over ethanol. Okay, ethanol is C2H5OH. So it will be 12 times 2 plus 1 times 5 plus 16 times 1 plus 1. Okay, so this one is number of mole. After calculation, you have number of mole, then you multiplied negative 1371. Okay, because this one is unit is kilojoule per mole. So you just eliminate the mole, then you can find the mass. Okay, so this one will be negative 342.75 kilojoule. Okay, so maybe I'm a little bit fast. This one is mole, this one is kilojoule per mole. Okay, so when you multiply this one, then you got kilojoule. Okay, so last part, okay, 1 mole of CO2 forms. Okay, 1 mole of CO2 form, that means the whole equation is just 1/2 times. So basically this one is 1371 divided by 2. Okay, so the answer for this one is negative 685.5 kilojoule. Okay, so not that difficult actually, but remember, if your answer statement is there, oh, how many kilojoule is released, say for example part C, okay, you may say, okay, 685.5 kilojoule released. You see that I didn't write negative here because release it represent negative already. Okay, so bear in mind this kind of presentations. So basically, our summary, okay, so we have C plus O2 becomes CO2. I have a delta H this part. Whenever we have this one and we have the state, okay, this one we call it thermochemical equation. Exam will just ask you to write thermochemical equation, then you have to do these features and these features. Features, okay, understand the conditions. The most important thing is about the standard state. O2, O, okay, we pick O2. Graphite and also diamond, we pick diamond. Wrong, we pick graphite. Okay, so that will be the standard state. So remember, state symbol is a must. Okay, this one, okay, to indicate, okay, when the reaction run once, okay, how will the energy changes, how the enthalpy changes. Okay, and also you must give positive or negative sign. Okay, even it is positive, you still need to have a positive. Oh, that's all for the introduction of thermochemical equation. Bye bye.